들리시죠? 네. 자, 제가 이번 주에 숙제라고 했나요? 아직 그때 바꿨나 한번 다시 확인을 해볼게요. 듀를 바꿨는데 그렇네요. 홈워크 5는 이번 주까지 듀고요. 다음 주에는 수업이 없고, 그래서 숙제도 없고, 그 다음 주부터 이제 또 계속 숙제가 있을 거예요. 자, 일단은 봅시다. 뭐야 이거? 자, 지난 시간에 오리엔테이션 얘기까지 했고, 이제 example이랑 problem 보면 되죠. 자, 일단은 복습을 한번 해봅시다. Okay, so last time we talked about the line integral and surface integral over vector field. So the vector field is a map which assigns a vector in a vector space to a space, a point in the space. Okay. So usually we take the same dimension for the vector space and the normal space. So upshot for this vector space is that if you have two vector spaces, vector fields, then you can add them or you can multiply by a scalar number. And also you can define a line integral of this vector field. So usually we take the different symbol for the line integral over vector field. So this symbol means that we are taking an integral over a line or a curve inside of two-dimensional space or three-dimensional space. And this symbol, which is the dot, is meaning it's a inner product between vector field and this infinitesimal amount of this line C, a curve C, with some with a direction and the size. So it's kind of a vector. So this is just a symbol representing the line integral. How we defined is the following. Suppose that we have a parameterization of this curve using the interval a to b, then this is defined to be f of ct inner product with c prime t dt. Okay. So unlike the line integral of the real valued function, we take the velocity vector of this parameterization and then inner product with a vector field at the point at time t. And also we talked about the surface integral. Suppose that we have a surface parameterized by some function x. So let's say D is a domain inside of Rn. So usually we take Rn, this dimension of space or vector, to be 2 or 3. And let's say this S is the space surface inside of the same space. I'm sorry, so this is the surface. So it has to be two-dimensional. Right, so this is 3. So when you parameterize your curve inside of two-dimensional space or three-dimensional space, you need one parameter. In order to parameterize your surface, you need 2 parameters. So your domain D must lie inside of two-dimensional space. And S can be lying inside of three-dimensional space or four-dimensional space, whichever space, as long as the dimension is bigger than 2, it's okay. So anyway, let's say we have a surface integral of a vector field. The notation is a little bit different from line integral. Instead of small s here, we have large S, meaning that it's the normal direction to the surface. And we're taking inner product with a vector field f. And we are taking integral, and this is defined to be the integral over D, where f x uv is in the inner product with this x. I'm sorry, so I used x here. It's a bold x. Okay, xu cross xv, xu cross xv. Okay, and then du dv. So basically, this is not the same as the integration by substitution. What we are doing here is that we have a surface inside of three-dimensional space, and for each point, which is identified with a point inside of UV plane. So this is UV point, and this is the point line identified by one-to-one map X on the surface S. And we are taking a normal direction to the surface. And this normal direction is perpendicular to the surface and also has a size 1. So we divide it by the length of the cross product here. So this is our xu cross xv divided by xu cross xv. So for each point inside of the surface, we take a small, we'll take the small area. Right, we take this, let me take a little bit of, go back to the slide here. I'm sorry, so I made a mistake here. So we have here, so if you, well, let's say, if you really want this, then okay, so let's say we have xu cross xv du dv. Okay, so in the previous week we had a definition with integral sign over S, right? Instead, we are taking integral over D. That means we have to take a substitution, meaning using the parameterization of S. So you can rewrite this equation, rewrite this definition. So as, actually this is the original definition, f composite x like this, where n is the orientation, meaning that it's a normal vector which is perpendicular to the surface at every point. Okay. So if you plug in that, that's so far here, but now you have to take an integration over S. So we have to take a small portion of each part of S, right? So at each point, I'm going to take a small pieces of surface S and then take this area of S and then multiply that with the inner product of the vector field at that point with the normal direction of that point. However, I can rewrite that equation using the integration by substitution, that the integration over d and then ds should be modified to du dv with the term that modifies the area. Okay, so du dv is the area corresponding to this area of the surface, and the ratio between the area between the small portion of S and corresponding portion of UV plane is different. It's not equals to 1. So this term modifies the term. So this is actually the JT, the absolute value of JT, where this D, let's say, let me write this X UV to be X UV, Y UV, Z UV. Okay. All right. So, yeah, when you have an integration over surface S, we need a parameterization, and then we need a modified term. This is not JT, sorry. This is not integrated by substitution. It's just a definition here. So we need this term. So basically, we have a canceling out here, right? So this part is N, okay? So this part is N. So ds is changed to du dv times this term, which modifies the ratio between the areas. And then, because this part cancels out, basically we can write our integration over vector field to be f composite x in terms of uv, not x, y, z or something else. It's just uv. And then inner product with normal direction, but this direction is a simple cross product, not normalized du dv. Okay. So if you parameterize your surface in a different orientation, suppose that you're taking v first instead of u, then you get a negative sign to the normal direction, right? Then basically you have a negative sign here, so every term becomes the inverse negative sign to the original value. So entire integration becomes the negative of the previous one. So when you have a orientation which is different, which is opposite direction to the original orientation, then the surface integral becomes a negative. So basically the meaning of this line integral and surface integral is the following. For the surface integral case, you're taking the flux of the vector field through the surface S. So when you think about the flux, it's like water flowing out from this surface. So you want to find how much of water flows out at the given time. Then you only need to check how much the water particle passes through the surface S to the perpendicular direction. So if the water flows along the surface, there's no flux, right? So you don't want to add the parallel direction of the vector field. You only want the perpendicular direction of the vector field. So this is the flux. Sometimes the surface integral is called the flux of the vector field over the surface. And what about the line integral? So if you think about the vector field, it gives the force field. And this force field makes the particle in this field to move along this surface or along this plane. And suppose that you want to move your particle, move along the specific curve C lying inside of this space, then this line integral gives the amount of work that you need to apply to this particle to move this particle along this curve C. Or in other words, if you observed that the particle is moved along the surface along this curve C, where the force field is applied by this vector field, then this line integral gives amount of work that the vector field have done to this particle. Okay. All right. So that's the summary. And let's look at the problems. So first, examples. If you have any question, please ask anytime. So once we know what's the surface integral and line integral, then what left is the Green's theorem, Stokes theorem, and divergence theorem. That's the main ingredient of this multivariable calculus. So as long as you understand these concepts, you're done. So in the example, we are going to integrate the vector field given in the slide along the surface, a sphere surface. So first of all, we need to parameterize our sphere. So sphere, let's say S is our sphere, is given by this equation. Now, if you want to, so sphere is a round, you cannot parameterize by a graph of function in terms of x and y and z. So in order to parameterize your surface in terms of graph of function, you have to split your sphere to the upper hemisphere and lower hemisphere. So in the upper hemisphere, this is done by 1 minus x squared minus y squared and plus square root of that. And on the lower part, you have to parameterize your sphere using negative square root of 1 minus x squared minus y squared. Well, that's okay, but if you're using this parameterization, it's hard to compute your vector field. So let's try to do this, and then I'm just showing you that this is not the correct way of finding the vector field in the hand. If you're using the MATLAB, that's okay, because MATLAB can calculate for you, but it's very hard to compute by hand. So if you used this parameterization, for example, if you use this part, then our domain of xy, it must be the unit circle, a unit disk, that's here, and also same thing for the lower hemisphere. And you have to split your integration. So first you take the integration, compute the flux over the upper hemisphere, and then flux over the the lower hemisphere. So let's take a upper hemisphere S1 and a lower hemisphere S2. So your integration of the vector field is split into two. And let's take the upper hemisphere first. So we had a parameterization using this graph. So I'm going to use x to be, let's say, d to the surface S1, where uv is mapped to uv and square root of 1 minus u squared minus v squared. So u and v are actually serves as the role of x and y, but I'm using different symbols so that this d lies in different space and s1 lies in xyz plane. So let's say I have f given in the slide there. So I have to substitute x, y, z is there. So this is u squared v squared plus 1 minus u squared minus v squared. That's x squared plus y squared plus z squared. And on the above we have x, y, z. Right? And we take the inner product. By the way, d, what is d? So d is this unit disk. X squared plus y squared less than 1. Okay? And then what? In the previous formula, we had x, so it's just bold x, xu cross xv, right? So here comes xu cross xv. I have to compute xu and xv separately. So xu is 1, 0, 2 square root of 1 minus u squared minus v squared, and minus 2u, and xv is 0, 1, 2, 1 minus u squared v squared 2v, right? And then you take the inner product. So before you take the cross product, you have to consider the orientation of our sphere. So the example says that in the first, before you compute the flux, it orders you to pick an orientation. So you have to pick an orientation before you compute the flux. So I'm going to pick my orientation to be the outward direction of a sphere. So which means that our normal vector will always be pointing outward. Okay. So we are taking we're taking a flux over the upper hemisphere. So when I take the cross product, so that my direction, the vector going outward, I have to take the cross product in the order of xu and xv. And du dv. Okay. Why? Because here we have x and y coordinates. And I said that this parameterization has uv, which serves the same role of x and y. So if I move along my u, we have a direction, this direction kind of. So we have x, y here. And if I move my x to increase, then I have on the sphere that the curve corresponding to this line on the xy plane moves along the sphere to this direction. So basically the tangent vector is kind of this direction. Right? And how about when I move my y to the positive direction? So then I have this direction, so it's kind of move along this direction. Right? So I have a tangent direction to this direction. So this is xu, and this is xv. So you can say that x is x1, xx or xy. But then if you take the cross product, you always have a right-hand rule that you have 4 fingers pointing the xu direction to xv direction. Then the thumb direction is the cross product direction. So in order to have an outward direction as a cross product, you have to take the order of xu cross xv. So if you take the xv and xu, then you can have the inward direction, so opposite direction. So when you do the orientation with an inward direction, you're not taking on flux, you're taking on minus of flux. So meaning that you're taking how much of the water or fluid flowing into the surface, not going out to the surface. So anyway, so we have to compute this long integration. It's doable, but there's one more problem. So because this one cancels out, one problem is that this gives a little bit complicated formula, and we have a D, which is not a square domain. So we have a disk domain. You have to use the integration by substitution to do this. So you have to do the transformation, a polar transformation, in order to compute this long integral. And then that's the first part of your integration. So you have to do the same thing for the S2. So suppose that you've done this, you can do this integration over S2. And if you want to do that, you have to be careful that the orientation of S2 is the outward direction. So even if you use the same similar parameterization x, using that uv goes to uv and minus square root of 1 minus u square minus v square, the orientation must be taken so that this cross product is the downward direction, not upward direction. So you have to take the cross product of xv cross xu. Let me write that in here. So for integration over S2, this must be xv cross xu, where x is not the same as this one, but almost similar, because we have to parameterize the lower hemisphere. Only the z coordinate changes to negative square root of 1 minus u square minus v square. Okay. The reason why we have to change the order of this cross product is that we want the downward direction. So we're looking at the sphere as a whole, one surface. Okay. So we divided that into two hemispheres only because we wanted to parameterize by the graph of functions. But originally, it's a one sphere, a one surface. So this surface has one orientation, which goes outward direction. That was my pick. Okay, you can choose your inward orientation. I choose my orientation to be outward. So anyway, if you separate out these two hemispheres, the orientation looks different, because one in the upper hemisphere you have an outward direction, which is the upward direction. And in S2, we have a downward direction. So in order to have a downward direction of your orientation, then you have to change the order of the cross product. Anyway, this goes long. So if you want to try this, you can do that. But let's not do this. I don't want to use this. I want to leave my sphere as itself and then just take the integration, normal integration. So let's try to follow the definition. So on the sphere S, we had the normal direction, the orientation n. So what is the orientation? So we have a sphere, right? And this sphere has radius 1, right? And here is our point on the sphere, x, y, z. So this orientation is the vector on x, y, z, which points to the perpendicular direction to the surface S. But then this vector, the yellow vector, the orientation, is exactly the same vector from the origin to the xyz, because this length is 1 and this direction is the same. So I can map my orientation n to be nothing but xyz. Okay. And also think about the vector field f. We are taking an orientation. We are taking a surface as a unit sphere. So what goes in the denominator is just 1. So x squared plus y squared and z squared is always 1 in a unit sphere, so there's no denominator here. So I can take this integration to be x, y, z. So that part is f at the point x, y, z. And then I'm taking a normal direction, which is x, y, z again. And ds. Okay? So this part is n. So what's the result? I'm simply taking an integration of x squared, y squared, z squared, which is real valued function, over the unit sphere. That's already done in our previous example. So we have a nice parametrization of sphere by the spherical coordinates. So we are going to take x r theta phi to be r sine theta cosine phi, r sine theta sine phi, and r cosine theta. And we know that this Jacobian r theta phi, xyz, xyz, r theta phi is r squared sine theta. Okay, so when I take integration over s, well, that's the parameterization of a not sphere. It's a filled ball, but we are taking a sphere. So sorry. So I don't need r. R is fixed as 1, so I don't need r here. R here. So right. Sorry. It's not an integration by substitution. It's just a parameterization of surface. Okay. And then let's take x theta and x phi here. So what's x theta? It's cosine theta, cosine phi, cosine theta, sine phi, and minus sine theta. Okay. And then when I take the partial derivative by phi, we have minus sine theta, sine phi, and sine theta, cosine phi, and 0. Okay. So when I parameterize my sphere with theta and phi, remember that theta is this guy and phi is here. So theta runs from 0 to pi, and phi runs from 0 to 2 pi. So I'm going to change my limits from 0 to pi and 0 to 2 pi of what? So this xyz lies on this unit sphere. So whenever you take the sum of square, this is nothing but 1, right? Well, actually, there's nothing to compute because we are taking an area of the sphere. But let's do this for example. So we are changing our integration. We are taking a surface integral of the constant function 1. And what comes here is x theta and x phi in a cross product of size and d theta d phi. All right. So what's the cross product? So normally if you want the flux, you need a cross product in the correct order, but we are taking an integration of our scalar function, so we are taking a size, so we don't need to care about the order of cross product. So anyway, when you do this in this order, theta and phi, then 0 pi, 0 2 pi. So the first factor is sine square cosine phi. And then how about second factor? So we have sine square it's a minus, so it's a plus, so sine theta sine phi. And how about the others? So we have cosine sine phi square and sine phi square. So basically we have sine theta cosine theta and sines and d theta d phi. So what's the size? You take the squares and take the sum and take the square root. So if you add this together, you get the sine fourth and plus we have sine square and cosine square. So you have sine square cosine square. So this is sine square. So basically you take the square root of sine square. So it's sine theta, d phi and d theta. So normally we have to take the square absolute value sign when you take the square root. However, we have theta from 0 to pi, so sine theta is always positive, so I omit this absolute value sign. So phi is 2 pi, so theta is a constant to phi, so I just take the integration of 1. And then this theta from 1 to 0 is 2, so it's 4 pi, which is the area of the sphere of radius 1, right? So you could skip this computation because using this notation, we basically know that this is the area of S, which is the unit sphere. So you immediately conclude that this is 4 pi, but I've done this calculation just to show you that the surface can be computed by the double integral also. All right, so this is very easy example. Let's do the problems. All right. This example, you can do this example using setting this f and g to be vector field of PQR, and let's say G to be vector field of ABC, and then just compute the left-hand side and right-hand side, and then compare that each coordinate of vectors are the same. It's not hard just to do this. For example, if you want to do for the first one, let me show you how it can be done. Just take f to be PQR. Okay, so these are three-dimensional vectors. So each PQR is a three-variable function, and let's say G to be ABC. Then what's this on the left-hand side? So this is nothing but del del x, del del y, and del del z inner product with f plus g, which is p plus a and q plus b and r plus c. So basically we are taking a partial derivative of pa, qb, and rc. Okay. Okay. So that's the left-hand side. So on the right-hand side, we have first we have to compute this, right? And then you have to compute f minus f inner product g, a curl of g, and so on, and then add them together and check whether the sum is equal to the left-hand side. So first of all, let's compute this. So this is a be C, inner product with F. F. What is F? So I have to think about this F. There X, there Y, there Z. So it's Rx minus QZ and PZ minus Rx and then QX minus PY. Okay. PX. I think that's a typo. Let me check after I compute this all. So this is minus PQR inner product with G curve G, which is CY minus BZ, and then AZ minus CX, and then BX minus BX minus AY. So let's compute the first part. Here we have A times RY minus QZ, B times PZ minus RX, and C times QX minus PY, and then minus PCY minus BZ minus QAZ minus CX, and minus RBX minus AY. So that's the right-hand side. Okay. I think the problem must be changed to the left-hand side of the problem must be changed to this. So it's gradient of F, gradient of F inner product G. So I think that's the correct one. So let me just finish the computation. Maybe not. So where's a minus here? So let's combine this. So we have AR and we have AR, okay. So we have ARY plus AYR, right? So here and here. And let's see, we have B and PZ. So and B and PZ, we have BPZ plus BZP. And how about CQX? So we have CQX plus CXQ. And we take the negative. So we have AQZ, and there's a QA, which is AZQ, right? And then we have BRX, and we have BXR, and we have CPY, and we have CYP. Okay. So it's look like. So look at these ones. So we have, we take this one first. So we have del X of CQ minus BR for these two terms, okay? And how about del Y? So we have AR plus CP, right? Minus CP. And then we have del Z of BP minus AQ. Okay, so now I got it. So this is actually cross product, not plus, okay? So there's a typo. So what is this right-hand part gives? So we have a partial derivative applied to each of these terms. So we can assume that this is done by taking a divergence of the vector field given by CQ minus BR, AR minus CP, and BP minus AQ, right? And this looks like the cross product of two vector field, right? So let's take a cross product here. So cross product of F and G is given by taking cross product I, J, K, P, Q, R, A, B, C, and then same thing for the taking determinant of the 3x3 matrix. So for the I coordinates, I can get this by these two. So I have QC minus BR. Here QC minus BR. And then what about J coordinates? So we have take the AR minus PC. And then for K, we have PB minus AQ. Okay. So these three terms are the coordinates for F cross G. Okay. And then we are taking a divergence of that vector field. So on the left-hand side, we compute this straightforwardly, and then on the right-hand side, we computed each of summation and then show that these two are actually the same. So there's a typo for the first problem. Here we have, this must be a cross product, not plus, okay? So I will change this. And I think the rest of the part is okay. So try this 2 and 3 using the similar technique, showing that FG are the vector field whose coordinates are P, Q, R, and A, B, C, and then show that left and right hand side are the same. Okay, so in the second problem, we actually explained that in the previous class. So divergence, let me re-say that in words. So divergence measures the amount of expanded area or volume per original volume. So it's not the absolute amount of increment, but it's the increment over the size of original area or volume. So if you think about the unit in the physics of this divergence, it measures the ratio of increment, which is the meter square or meter cube over the second, over the meter square or second. Okay, meter cube or meter square. Okay. How about the kerr? So kerr measures how much the particle rotates around that point by the vector field F, and it also measures how much the work has to be done around that point per area that's surrounded by that circular region. So it's not absolute value of work that has to be done around that point. It's the infinitesimal amount of work per area surrounded by that circular region. Okay, circular path. So basically, this is the three-dimensional vector. So what I just explained is the meaning of the rotational a rotation of the vector field, the vector two-dimensional vector field. So this three-dimensional vector field, each coordinate has that meaning. So meaning that the xy and yz and zx plane, you have some rotation of some rotation going on used by the vector field f, and each amount represents the amount of work that has to be done around that point to rotate a particle for one cycle of circle per the area of this disk surrounded by the circular path. So anyway, you can look up the previous lecture to modify that explanation. And think about this problem. So this is very challenging ones, but once you know this, and you can do these more challenging problems. So what you are seeing here is the area bounded by three cylinders. So one is parallel to z axis, and this one is parallel to x axis, and this one is parallel to y axis. I have actual figure. So I'm not sure if you can see this, but let me change this one. So this is the figure that's shown in the slide. Okay. Well, how does it? Why is it surrounded by three cylinders? So look at this one. So this is the circle, right? Round circle. So this is one axis, and how about I change it, rotate that to 90 degree, then you get another perfect circle, right? Circle here, and then I'm going to rotate 90 degree another axis, so I get another perfect circle. Okay, so the reason I get a perfect circle is that it is bounded by a cylinder. Okay, so I don't care about the other axis, just in this axis, this becomes a circle. Okay, and as a whole, this is what it looks like. Okay, let's try to get the volume. So this is symmetric figure. So you have to imagine your three-dimensional volume in your head in order to compute this. So think about a projection of this figure on XY plane. So you have a round circle in XY plane. So that's a projection. And just to look at this portion, okay, so only for the pi over 4 parts, okay, I can only compute the area of the volume whose projection is this piece of pi, and then multiply that with how much? So we have 1, 2, 3, 4, 5, 6, 7, 8, and then I have upper parts and lower part, which is perfectly symmetric. So I can multiply that with 16 of the part that above this XY plane over this area. So we can compute what? Let's say this is our D. So over here, the coordinates of Z is bounded by one of the cylinder, one of these two cylinders. I'm not going to compute that yet, but anyway. And then dx dy, and then multiply that 16, okay? So what comes here is the minimum height of the coordinate of Z, okay? So one cylinder passes through this area on this direction, right? And another cylinder passes through this direction. Okay. So on the yellow cylinder, Z is parallel to Y, so Z is equals to minus x squared. So that's the maximum height that can go up to the cylinder. And how about in the blue ones? We have Z is equals to square root of 1 minus y squared. Okay. So I need to take the smaller between these two numbers inside of this area D, because that's the bounding surface of this volume. Think about the point inside of D. So if I pick any point x, y inside of D, x is always less than, so this is y equals to x line, right? So in this part, x is always bigger than or equal to y, right? So which is smaller? This one is smaller, right? So x is bigger than y, so 1 minus x squared is bigger than 1 minus y squared, right? So I have to take this one as the height of this area. So I have to take square root of 1 minus x squared. And then compute this. Right? That makes sense? So let's parameterize our D using the polar coordinates. So we have x, r, theta to be r cosine theta, r sine theta. Now the range of r and theta is not entire surface, so r only ranges from 0 to 1, and theta only ranges from 0 to pi over 4. Right? Okay. So this computation 16 times. So let's plug into the formula. 0, 1 for r and 0 to pi over 4 for r. And then what? Inside of here, 1 minus r squared cosine squared theta. And then we have to multiply the Jacobian. XY first. XY r theta dr d theta. So this is x and y. So if you compute this, you know that this is r. So we have 16, 1, 0, pi over 4, r, 1 minus r squared cosine square r, dr d theta. And I think it's easier to compute the integration r first. Sorry, I have to change this to theta r. So also here. Pi over 4, 1, and theta r, right? So this is 16, 0, pi over 4, Let's see. This is 1 minus r square cosine square 3 over 2, 2 over 3, and then 1 over 2, minus 1 over 2. Cosine, forgot the cosine. Okay. Then I get this one, right? So canceling out 2, 2. And this run from 0 to 1 for r and d theta. So this is 16, 0, pi over 4. So when r is 1, this is 0. So when r is 0, not 0. So when r is 1, this is 1 minus cosine square 3 over 2. And then when r is 0, that's 1, minus 1. And then we have minus 1 over 3 times cosine square d theta. Okay. So this one is sine square, so it's basically sine cube. Okay. And then let's see. It's a 16, 0, pi over 4 times, let's take out this 1 over 3 here. And we have cosine square, and that's 1 minus sine cube d theta. I know that this is simple computation, but let's use the MATLAB. Okay, so here sims theta, and I want integrate 1 minus sine theta cube, and cosine theta cube for 0 to pi over 4. Okay, so that's the result. So it says, let me write that out. 3 minus 1 over 2 times 3 square root of 2. Okay. So we have 3, 3, 3 cancels out. And we have 16 minus 8 square root of 2. That's the volume. Okay. All right, so let's look at the other ones. Oh, is that all? Well, that's it. That's the end of the problem. Okay. Any questions? All right, so this is now week 11 this week. So before we start from the definition, let's briefly look at what we're going to talk about this week. So basically, we're going to talk about several properties of vector field and definitions. And also we are going to talk about the line integrals more thoroughly. So remember that we talked about the line integral in this kind of notation here, like this one, like this kind of notation, right? But also we can talk about the line integral here using dx dy notation. So we're going to use this notation also frequently. So like this one, like this kind of notation, okay? So that's our objective to this week. So let's look at the definition first. We're going to have lots of definition and lots of proof this week. So first of all, let's say we have a two-variable function defined on the region in two-dimensional space. We're going to define a gradient vector field of this function, whose vector value is defined to be the gradient vector. Now, it's easy to construct a vector field out of a two-variable function. Suppose, conversely, we have a vector field defined on the region D. If there is a function, two-variable function phi, satisfying that the gradient vector field is equal to the original given vector field f, then we say this phi is a potential function to this vector field f. Okay? So you probably learned the potential function in the physics, like in classical mechanics or electrodynamics. So it measures how much the work has done by this vector field. And this function actually gives the vector field by the gradient vector. So here's another definition and theorem. So suppose that we have a vector field f whose coordinate functions are p and q. This is two-dimensional vector field. If qx minus py is equals to 0, then we say it's closed vector field. So in other words, if the rotation of the vector field f is 0, then we say it's closed. Okay? Now, the theorem says the vector field admits a potential function, then it is closed. So admit means that there is a potential function to this vector field. So proof is very simple. If you have a vector field and there is a potential function, then we have pq equals to the gradient vector field of phi. Then we take the qx, which is phi yx, because q must be phi y. So we have another second partial derivative in terms of x. So we have phi yx. And we have p equals to phi x, right? So we have py is the second derivative of phi, first by x and then y. So we have phi yx and phi xy subtract each other. Now normally we have two second partial derivative. They are not equal as long as if we assume, if it is equal as long as your second partial derivatives are all continuous function. We didn't assume that, but actually this theorem should assume that continuity of second partial derivatives. So we didn't say anything about the differentiabilities or continuity of second order derivatives, so on. So throughout this chapter, or throughout from now on, we always assume that our vector field or a function has a coordinate function which is continuous, differentiable, and second order partial derivatives are all continuous. So you don't have to worry about the counterexample that we have seen in the pre-midterm, that sometimes the second partial derivative doesn't match each other and so on. So it always works, okay? So it doesn't matter whether you take the y first and then x, or x first and then y for the partial derivative. They are all equal. Just think about this phi as if it's a polynomial function or exponential functions. Okay, don't worry about the counterexamples. All right, so we talked about the vector field who has a potential functions and also closed vector field. So we have two properties of vector field. One is sometimes it has a potential function, and the other is sometimes it is a closed vector field. There's another definition, another properties of vector field, which is called conservative vector field. So a vector field is called conservative if the line integral does not depend on the path, but only depends on the point it starts and ends. Okay. So the important part is that this curve must lie inside of the domain where the vector field is defined. Okay. So as long as the path is defined inside of the domain of definition of the vector field, then it says the line integral, or in other words, the work that's done by the vector field does not depend on the path, but only depends on the starting point and end point. It's like the work done through the gradient vector, gravitational vector field, right? If you're taking the heavy object from the ground to the sky, it doesn't matter which path you take this mass to the sky. It only depends on the height of the act, right? So in other words, a vector field is conservative if the line integral over closed curve is 0. So what is closed curve? Curve is called closed if the start point and end points are the same. So let me write that in boards. So we have a curve C start from P to Q. Okay. So if it doesn't depend on the path, let's say C1 is this path from P to Q, and C2 is this path from P to Q. If the line integral is same here, then I can move this integral over C2 to the left-hand side and then rewrite this as C1 minus C2, right? But then I can rewrite that as this. So minus integral over C2 is minus of work done by moving particle from P to Q along the C2. But I said that the line integral over vector field is negative if you take the inverse direction of the same path. So this minus C2 means that I'm taking a path from Q to P, right? So this line integral path is P to Q along C1, and this integral path is the path from Q to P along C2. So basically we are taking a circular path starting from P and end up with P. Okay? So we have always this line integral equals to 0 as long as it's closed. So in other words, conversely, if you have always the 0 line integral for the closed curve, then let's say we have P and Q here, and we take the circular path starting from P and then getting Q at somewhere and then come back to P again. So this is our circular path C. So this is closed, so we know that this is always 0, but also we can rewrite this C into two pieces, which is C1 and C2 here. So it means that C1 plus C2 is always 0. So let's take the C2 integration on the left-hand side. We get minus of C2 equals to C1 integration. So that means that C1 integration P to Q is equal to negative of Q to P. But the negative of Q to P integration along the C2 is equals to the integration over P to Q along C2 in the opposite direction of C2 here. So basically this is minus C2 is equals to C1, but the minus C2 is actually a path from P to Q, not Q to P again. So we know that this two integration along these two different paths are the same, but these two paths have the same starting point and end point, so we can conclude that this vector field is conservative. All right, so here's a theorem, important theorem, that the vector field admits a potential function, then it is conservative. Okay, so like a gravitational vector field has a potential function, which is a potential energy actually, and it is conservative. So proof goes follows. So we have a two-dimensional space, so we're only talking about the two-dimensional vector field. Let's say we have a curve CT given by xt and yt, and it's a parameterization of C from one point to another, okay? So we're going to show that this is conservative, which means that this line integral over C is always depending on the starting point and end point, P0 and P1. So let's rewrite this line integral in terms of another notation here. So we assume that this f admits a potential function. So first coordinate of f, the vector field, is phi x, and second coordinate function is phi y, right? So this phi x dx plus phi y dy is the vector field. I mean the integrand of this line integral. So there's a typo. So let's rewrite this del phi del x and then del phi del y, and then now let's rewrite our parameterization in terms of t, and then this dx dy becomes del x del t dt and del y del t dt. Okay. So by the chain rule, we have the integrand, which is actually equals to the derivative of phi composite with the parameterization of c, and in terms of derivative in terms of t. So this whole thing, so there's a typo again, so there's no x here. So there's a so we have d dt of phi composite c, and then dt again. So dt is already here. So what we have here is nothing but taking a derivative of phi, which is the function of t, and then take the integration again, right? So by the fundamental theorem of calculus, this is exactly same as this difference between the original function, which is the antiderivative of this integrand d dt phi, from the point at t equals to b and t equals to a. So when t equals to b, we have p1 point, right? And when t equals to a, we have p0 point. So this is exactly here. So what we have computed is that the integrand line integral is same as the difference between the potential function at the starting point and end point. Okay, it doesn't matter. So this result doesn't depend on the parameterization of C or the shape of C. Only depends on the starting and end points. So it's a conservative vector field. So, and it's a simple corollary that it's a vector field that admits a potential function, then if you take any closed curve, then the line integral over the closed curve is 0, okay? Which means it's exactly the same as conservative vector field, okay? So let's look at this example. It's a very important example. So we have D, which is the first quadrant of the two-dimensional plane, and we have a function theta given by arctangent of y over x. And this becomes the potential function of the vector field A. Okay. So let's look at this by this in the blackboard. All right. So we first want to check whether this theta function is actually the potential function to the vector field A. So arctangent of y over x. So I assume that my domain does not contain any of the coordinate point whose coordinate x is 0. So it's well defined here. So let's say theta x is 1 plus y over x squared of derivative of y over x, which is minus x squared y. So when I take the x squared multiplied together on top and bottom, we have x squared minus y. And what about theta y? We have 1 plus y over x squared, and then x, 1 over x. So we multiply x squared on top and bottom. We have x squared plus y squared and x here. So this is the x coordinate function for the vector field A, and this is the y coordinate for the vector field A, okay? And now think about, again, we know that this is the potential function now. So it says that whenever I take a path inside of the first quadrant here, from one point, let's say P0, to another P1, it does not depend on the shape of the path, but only depends on the starting point and end point, the value of the line integral. So we have these 2 points, and this is, let's say, C, and this vector field A, line integral, only depends on starting and end. How do you want to compute this? So what's the value? So let's say P0 is x0, y0, and P1 is x1 and y1. So the value is actually this difference between the value of potential function. So we have y1 over x1 and theta y0 over x0. So what does it measure here? We have arctangent of y. I'm sorry. What am I doing here? So this is just a two variable function. The value of that function is given by this. So this is x0, y0, x1, y1, and arctangent of y0, x0, are arctangent of y1, x1. And what about this? Sorry. So 1, 0. 1, 1, 0, 0, 1, 1, 0, 0. So that measures the angle of this P1 from the x-axis. So this is theta 1. And how about the second summation? That's the measure of angle of the P2, P0. I'm sorry, it's a P0 here. Right? So this is theta 1 minus theta 0. So it's a difference of angle at P0 and P1. Right? So this vector field A always measures the difference between the angle of starting point and end points by the line integral here. Okay? Doesn't matter how far these points are away from the origin. It only measures the difference of angles. Okay, so let's look at this example. It's also a very important example. So we have a same vector field A. Oh, sorry, I changed this to slide. All right, so we have a vector field A, and now we change the domain of definition of this vector field. At the previous example, we had a domain of definition on the first quadrant of two-dimensional space. Now we are going to take the the domain of definition to be entire space, entire two-dimensional space except 0, 0. Because when x and y are both 0, the numerator here, denominator becomes 0, so it's not defined. So as long as x, y are not both 0, this vector field is well defined. Now think about this vector field. It's closed, right? Why? Because if you take the partial derivative of this part by x, and then take the partial derivative of this part y, and then subtract each other, you can get the 0, okay? Now, it's closed, but does not have a potential function, okay? It might be confusing, so let me summarize what we have seen in the definition and theorem so far. So let me write that in the board. So we have 3 properties of vector field. First one is admitting a potential function. And the other is closed, and the other is conservative. Okay. So we show that if it has a potential function, then it's closed. Okay. That's the easy part. And we also show that if it has a potential function, then it is conservative. And we also see the examples. But look at this one. So we have example that says a vector field is closed but does not have potential function. So it says that the converse of this direction doesn't work. Okay. Why? So why A does not have a potential function? We had a potential function theta here in the previous example, right? Why doesn't it work here? Because although the vector field are the same vector field, why can't we use this theta function to be a potential function? So answer is on the domain of the definition. So here on D, where x and y are both bigger than 0, this vector field A, which is minus y over x squared y squared, x over x squared y squared, has a potential function theta, which is given by arctangent of y over x. On the domain in two-dimensional space where x, y are not both equals to 0, this A does not have a potential function. First of all, this potential function doesn't work because it's not defined when x is 0, right? But in the domain, our new domain, it contains a portion of y-axis. So here, although it omits the origin, but here we have x equals to 0. So theta is not defined. Okay? And you might ask that, well, maybe that's because you take the arctangent to measure the angle. When you have a point lying in this yellow line, the angle is pi over 2. So we can use the cosine inverse or sine inverse to measure the angle of the point in here. So you might try to use another inverse trigonometric function to measure the angle. You may try, but I'm telling you that it does not have a potential function either. Anyway, in any method you choose, your angle doesn't serve as a potential function defined on this entire domain D. Let me explain, logical explanation why it cannot have a potential function. If it does have a potential function, if it has a potential function, then because of this implication that if it has a potential function, then it must be conservative. For any closed curve C inside of this domain, the line integral must be 0. In other words, I can choose my closed curve inside of domain D, which now it's an entire plane except the origin. Let's choose that as a unit circle here. Okay, starting from zeta equals to 0 and end at the same point. So I'm going to parameterize by cosine t and sine t. Now, however, what's the line integral? It's a 0 to 2 pi, so line integral of that curve of A. What was it? We actually computed this in 2 weeks ago, or 1 week, or last week, or maybe. What was the integration here? If you forgot that, and then we can compute it again. So we have A, which is, denominator is always 1. We are in a unit circle. So minus sine t, cosine t, and then C prime t, which is minus sine t and cosine t dt. So basically we have sine square plus cosine square, which is 1, so 0 2 pi of dt, so it's 2 pi. It's not 0, okay? So line integral over this closed path is not 0. So it cannot be a conservative vector field. So it's a contradiction. If it has a potential function, it must be conservative, but doesn't. It doesn't satisfy the properties of conservative vector field. So this is a contradiction. Okay. So usually the converse direction of this implication doesn't work, but sometimes it works. So here's a theorem. Sorry. So sometimes it works. Why the green theorem comes up here? So let me look at the Poincare lemma first. In order to prove this lemma, we need a green theorem. So that's why I put this green theorem before I prove that. So look at the Poincare lemma in the slide 10. Now, suppose that D is simply connected region in R2. I didn't define what simply connected is, but let me read out the theorem and then explain what simply connected means. And F is a vector field defined on D, If f is closed, then f admits a potential function. So exactly the converse of that implication, right? So our assumption is that the domain of definition of this vector field is simply connected. So what is simply connected? So easy definition, a region D inside of R2 is called a simply connected if it has no hole. Okay. So for example, let's say D to be the first quadrant inside of R square is simply connected. What about the domain that we have chosen in the second place? So we have xy inside of R2, but xy cannot be both 0. This is not simply connected. Okay. Why? It has a hole, the origin. Origin is missing inside of the entire domain. So the more rigorous definition of simply connectedness is the following. So whenever you have a domain and you choose a circular path or closed path, in other words, simple path, that it does not intersect each other, but it comes back to the original starting point. If you can shrink your loop, it's called a loop, that doesn't intersect each other, but also it comes back to the original starting point. It's called a loop. If you can always shrink your loop into a one point continuously inside of this domain, then it's called a simply connected domain. So for example, if you have a first quadrant, so like all entire first quadrant, then if you take the loop inside of first quadrant, you can always shrink your loop into a one point inside the first quadrant. However, if you take the second domain, whose origin is missing here, you take a loop. This is the one loop. You want to shrink this loop into a point, but you cannot do this continuously because at some point you have to jump through this missing point. You cannot shrink your loop into a point except you kind of break one point of the loop and then reconnect it again here. So this is not simply connected. So Poincaré's lemma says as long as your domain is simply connected, the converse is true. This is true if D is simply connected. So if D is simply connected, then the closed means that it has a potential function, and naturally it's a conservative, right? All right. So let's look at. Let me summarize this. What's left in here? Right. So I'm going to talk about the Green's theorem later. So before we prove this, let's summarize what we have in here. So we have potential function, having a potential function, and have closed vector field and conservative vector field. So this is having potential function is the strongest condition that vector field can have, and if it's closed, then in general we don't know anything about that, anything except that it's closed. But if you have a domain who's simply connected, then we have all these three implications. And having conservative vector field means that, let's see, there should be one more theorem. So having conservative vector field, let me read, so go back to here. I think I forgot to mention this. So conservative potential. So if D is simply connected, simply connected, potential function is closed. Right. So if D is simply connected, then closed means it's conservative. So that's the corollary of the Green theorem. So having the simply connected region as the domain, we have all three conditions for vector field are all equivalent, which means that you can assume one and the other follows naturally. So if you don't have a simply connected region, then you have to be careful what kind of condition that is given on the vector field. So if D is simply connected, we have this converse implication. That's the Poincare lemma. And this part, when D is simply connected, then it's closed, implies the conservative comes from the corollary of the Green theorem. And once you have this yellow guaranteed, then you have closed potential function are the equivalent condition, and closed and conservative. What's conservative? This is actually true. It doesn't really matter here, right? Closed, conservative. This is actually this should be, if it's conservative, then it has to be in this direction. I think I made somehow I think some statement must be missing here. So if D is simply connected, then the conservative implies closed. So all three things are equivalent, right? So it's a circular implications here. So let me change the slide a little bit. Maybe I omit some of the important remark here. So anyway, so we have this lemma that we are going to cover next time. And let's look at some examples. This one is after we've done the Green theorem. It's also a Green theorem. But let's see, let's look at this example. We don't need the Green theorem to compute this. So here, this one. So we have C be the semicircular arc from 0, 2 to 0, negative 2. So we have I didn't say that it's upper semicircle, but just let's assume that this is upper semicircular arc. Okay, so it's also counterclockwise. We want to evaluate this. So now this line integral is given something like scalar integration, but it's not. It's a integration over vector field. Okay. So I just want to tell you that this kind of notation can appear in many places. So I want to train this kind of computation. So we have integration of c xy squared dx minus xy dy. So in other words, this is actually equals to xy squared minus xy ds integration. Okay, so I'm assuming that this c is this 0, 2. So we have this, okay, 0, 2, and 0, minus 2, right? So I have to parameterize this curve C. So Ct is equals to cosine t and sine t. 2 times of cosine t and sine t. And t is from pi over 2 to 3 pi over 2. So pi over 2, 3 pi over 2. And what's this? It's cosine t sine squared t minus cosine t sine t. And then minus 2 times sine t. I forgot 2 also. So 8, and this is 4. And then this is 2 sine t cosine t and dt. Okay, so you can rewrite your definition of this vector line integral again, and then try this. But also you can simply using this notation to compute directly. So this is following the definition, original definition. And if you just want to follow this kind of notation, then simply take pi over 2, 3 pi over 2, and plug in x and y with this parameterization. So 8 cosine t sine square t. And then now dx becomes dx dt times dt. Okay, so just simply multiply this derivative in terms of t with dt. So it's 2 minus sine t, and then minus 4 cosine t sine t, and then dy dt times dt is dy. So this is cosine t 2 times cosine t, and then dt at the end. So it's a long computation, but doable. You can do this by maybe some trigonometric properties. Okay. However, the next example is hopeless. You cannot do by parameterization, so you need a green theorem. We will do this next time. And also this requires a green theorem, but it's very interesting because you see that there's points of vertices of n polygons are given, and the area can be computed by just a polynomial expression of these coordinates, right? It's very interesting, but it's also done by green theorem. Let's look at this one. So we have problem. F is given by 3y minus 4x. This is a vector field, and we want to compute the line integral over this circular path. So this delta D is the boundary of D. So D is the two-dimensional region. I want to take only the boundary. Okay. So it's not hard, but let's look at the second one. It's a circular path, so you can always parameterize by cosine and sine. How about this one? So you have a elliptic circle, okay, elliptic area. So in that case, you can always parameterize also by cosine and sine. Here we have problem. I have a vector field 3y minus 4x, and then I want to parameterize this by 2 cosine t. Now, in order to have x squared plus 2y squared equals to 4, I need sine t for y, right? Square root of 2 sine t. Right? That's a parameterization of the elliptic curve. Okay, so now let's try to compute the line integral. So let's assume that we are loop around this elliptic curve once. So I need theta t runs from 0 to 2 pi, and then we have 3 square root of sine t and minus 4 times 2 cosine t, and then inner product with minus 2 sine t and square root of 2 cosine t dt. Okay. So we have 0 to 2 pi of minus 6 square root of sine squared t and minus 8 square root of cosine t dt. Okay, a square. So you have to compute the integration of sine square and cosine square, and you get the result. Let's look at others. Okay, so we have a problem. Evaluate where C is the cardioid. R equals to 1 minus sine theta. Sorry, I have to change this. 1 minus sine theta oriented counterclockwise. So there are two ways to solve this problem. Easy one is using the Green theorem. I didn't mention that yet, so we're going to do that next time. So other way is just following the definition of line integral. So we have a parameterization given here. So we can take R to be 1 minus sine theta, and x coordinate is multiplying cosine theta, and y coordinate is multiplying sine theta. So and then plug in that here, and then run from 0 to 2 pi, you get the line integral. So let's do this. Are there any other problems? Okay, well, let's do this one. There's no time here. So it's almost over, so it's the 50. So let me do that in the next time. So anyway, so let's also do this in next time. So this problem, you also can do this by Green theorem or simply taking a line integral here. But this kind of problem uses the notation of dx and dy, notation of line integral, very efficiently. So when you have this kind of line, okay, so you have a left to right straight line, then y is fixed along this curve. So you have no dy term. So along this line segment, you can only compute the line integral of this part, okay? And how about this part? You have x fixed, so dx is 0. So you can only compute the line integral of this part. So that's what I wanted to show. Let's do that in the next time. All right, so thank you for listening, and if you have any question, please ask anytime. So see you on Friday. 자, 질문 있으면 하시고요. 오늘 한 내용 한번 다시 복습해 보시고, 지금 뭐 그린 시어렘이랑 요거 시어렘 프루프하고 나면은 문제 푸는 거밖에 안 남아 있거든요. 그러니까 뭐 미리 푸셔도 돼요. 뭐 이건 어려운 건 아니니까. 숙제 오늘 이번 주 금요일까지 지지난번 숙제 하시고요. 질문 있어요? 네, 고생하셨습니다.